turns out people like Star Trek might also be tech people.
Yeah.
Game of Thrones, there's a lot of those guys too, but.
Also, HBO has more than one good show.
That's true. That's true. And when you pay for HBO, you all. So I'm gonna have to delete this all out of the video. When you pay for HBO, you get no commercials.
Yeah.
Which is also true legally done.
So now you're paying money and also watching commercials.
Yep.
Yeah. I don't see how that business model is going to work well. So.
What service is it on?
CBS's special wannabe Netflix.
Yeah. Hulu that too? You pay for it, but you still get commercials?
You pay for it and get commercials, or you can pay more and get less commercials.
No, you can't get any.
Really?
I pay the premium.
Did you pay the premium? Because I looked at that and it said no commercials, but maybe sponsorship something afterwards. So I was like, I don't know about that. Okay. So did you watch Star Trek? It actually was really good. If you're a Star Trek fan, it was really good.
Yeah, we're such dorks. We're rewatching like Deep Space Nine right now.
Yeah, the best one.
Yep. I'm not kidding. That's why we had
It had a
Hulu.
slow first season.
It did.
It had Hulu, so that
But not
we
a
can-
cheesy first season like TNG. But I was a really big dork. I had them all on videotape, but I would even tape myself. All right. So thankfully, I think we're gonna get through this pretty quickly today. We only have 3 real topics to talk about until we finish the networking portion, not including routing, because we're just gonna spend a lot of time on routing, but not including routing. So,
We will cover routing?
huh?
You said we will cover routing?
Yeah, we're gonna cover routing a lot,
Okay.
right? It's hard to, like, a lot of the research actually area is in routing, and a lot of like DDoS prevention is in routing, and everything is in routing, right? So we'll get to that. So, but for the general networking later, we're gonna presume right now that we have hard-coded routed or some magic routing black box that just does that for us, and we'll talk about that black box later. But for now, we only really have 3 more topics to cover. We talked about fragmentation last week, and we said if a packet was fragmented and we had the DF flag flipped, right, it simply runs into the router sends back an ICMP message, and the packet's dropped.
Mm-hmm.
So that really leads us to what the heck is ICMP and what's it actually used for. So one of the things, obviously, is to be able to find a point-to-point maximum packet size. But it has some other things as well. So we have computer A talking to computer D. We're down to brown. Talking to computer D. And obviously there's some middle box in here. So the question is, when we talked last week, right, we would send something across, and we have the DF flag. It reaches, say, this point here, and this router says, I can't do it, and sends back an error message, right, through ICMP. But obviously, we can use that functionality for any error, right? It doesn't necessarily, we don't have to have one dedicated protocol to send back simply that, a maximum MTU, right? So we can use it for other errors, obviously. And so the question becomes is if we encounter an error, right? Obviously, this box needs to know how to interpret the error, and at least this box needs to know how to send the error, right? So this is actually adding functionality to all the network layers, right? Which is important because we're going to talk about middle boxes at the end of today, where they add functionality to one box and achieve different results. So ICMP is actually really, really simple. So ICMP just has a couple of fields. It has an ICMP header, which has the type, the code, and a checksum for the ICMP packet, just in case on the way back something bad happens. And we discussed last week as well that and this is I think this happened at the end of class, was what happens if the ICMP packet in our error example last week with DF flag drops? What happens?
Well,
Remember the packet was killed here and it sent back an ICMP message. What happens if the ICMP message is dropped?
We don't know that it didn't go through.
We don't know that it didn't go through, right? But conveniently, it doesn't matter because what will happen is A assumes that it was a packet drop, right? And so we reach the timeout and we send another packet. It's still too big, right? But it reaches here. There's the packet, there's no state table or anything keeping track of these things. So the packet reaches here, it's too big again, it sends out another ICMP and drops the packet again. And it just pick up right where it left off. Right? So there's no problem, there's no extra functionality that you have to build in to get the to ensure that the ICMP packet reaches. Because it just works. So the biggest things that you're going to deal with ICMP is a fragmented packet, which we talked about last week. What other things do we need to deal with?
if destination unreachable.
Destination unreachable, right? The most frustrating of ICMP packets,
Mhm.
right? Your network is broken. I have no idea how to get here.
And also it shows the round trip time, right?
It shows at least time to live.
TTL.
Yeah, which actually isn't a time at all, it's really hops to live. And when we talk about IPv6 here very shortly, they've actually renamed that field to hops to live. So what's the actual purpose for time to live?
So the packet will not go forever.
Yeah, so there could be loops inside of your network, right? Somebody misconfigured something, somebody wrote a bad routing algorithm, something, and you have a loop inside of your network. If you have a loop inside your network and there's no time to live, then the network, that packet will live forever. Right? Provided somebody doesn't turn the power off or disconnect the cable, it will seriously live forever. Right? So, or I guess your address can be corrupted eventually, right? But even just simple corruptions won't kill it because it will be inside the data field. And these routers aren't actually checking the packets, they're just forwarding. So a time to live simply works by every time it passes through a box in the network, it decrements that value. And when it gets to zero, what do we do? Bit bucket, right? Do the exact same thing that we did with a packet that was too big and the DF flag flipped, right? You simply drop it. Now, what is time to live most often used for? That was the,
How
huh?
many hops there are?
Yeah, it's used for trace route. So right now we built an architecture where the entire network is self-sufficient and completely distributed, right? There's no central management to this network. Each box exists and runs on its own. So the question is, how does A, if they're trying to troubleshoot problems, figure out how I actually got to D,
piggyback.
Huh?
By piggyback, or what do they call it? Yeah, piggyback, right? So when A sends a message to D, D sends an acknowledgement that routes that trace back, and it's in the header.
No, so when A sends a message to D and D sends an acknowledgement, D also doesn't know how it got there. Remember, we're not changing any packets as we go through this network, right? We might be changing the link layer packets, right? Moving from one different type of network to a different type of network, but the IP layer is staying the same, right? And so, and there's no state that's being kept track of in these packets, right? So if we move from this is on Wi-Fi 802.11, right? And then this length is 802.3, and this is like some, like, probably better to switch that, right? The only thing that this D sees is the last state. There is no state tracking. So the question is, how do you, and the hint is time to live, how do you find the route through the network? It's not necessarily the route the last packet took, but it is a route through the network, which is more than likely the last route that was taken.
Just like send packets with like TTLs or like incrementing numbers?
Correct.
Or just
We send an ICMP packet out ourselves, and the first one we send out is with a TTL of 1. When that reaches the router decrements it and does what? Drops it and sends back an ICMP. I dropped your packet, right? And then I send out another one with the time to live of 2. It makes it through the first router, gets decremented. What happens at the second router? Drops it, sends back a message. I dropped your packet. These messages are when ICMP comes back through the network. So we didn't talk about this last week, but when the ICMP for this router, for whatever reason, whether we're doing trace route or whether we're doing flipping the DF flag to find the MTU through the whole network, whatever, when this packet comes back, what, if this is A, this is B, and this is C, what is the IP header for this? So the original packet that came through was AD, right?
Yep.
For source and destination. When the ICMP packet comes back, what is it?
CA.
It is CA. The router itself sends back the ICMP packet. So if the router itself sends back the ICMP packet and you're doing a time to live, what's the first, if you have a TTL of 1, right, and you say AD for source and destination, then your return packet is what?
BA.
BA. And then we do a 2, right? And you get what?
CA.
CA. And so on and so forth until you traverse the whole network.
And we incremented the time tell by 1, right?
Huh?
We incremented the time tell by 1.
We increment it by 1 every time. And so we send multiple packets through the network trying to reach D until it actually is delivered. When it's actually delivered at D, we know we've got our complete route. Now, if you actually open up trace route, for the guys that have Macs, you can do that right now and do a trace route to Google. Some of them will not reply.
Mm-hmm.
Because sending back an ICMP message is optional. So some of the routers simply don't do it. And if they simply don't do it, then what will happen with your ICMP packet when the time to live dies? It gets dropped. No ICMP back. So traceroute takes that into account in a timeout. So you'll watch you'll watch traceroute go bang, 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 address, and then it will pause. And it's waiting for traceroute's own timeout to wait to see if I didn't get a packet, and you might try a couple times just to make sure that nothing happened inside of the network.
Is it when we have stars?
Yes, in traceroute it'd be stars.
Okay, as far as I understand with the star, that's, okay, I'm getting your packet, I can deliver it to the destination, but I'm not gonna share their information.
Yeah, I'm not going to share my information with
Yeah.
you. Correct.
Okay.
So what happens if ideally you like send out these packets and they go the same route every time? What if like some packets go in different ways, so like it doesn't go through the same route?
It is possible, yeah, that's what I said, you're saying it's a probability that this is the correct route. Now, huh?
Traceroute will actually send each TTL 3 times, so you can see if that's happening.
Okay.
And then the last part, ICMP functionality is ping. Right? Are you alive? Which also may or may not be replied to.
Mhm. And why is security just like, or recommended that you not enable the ICMP?
Because it allows you to quickly scan a network to identify targets. ICMP is super fast. It's almost always implemented. It's almost always turned on, and it allows you to rapidly scan an entire network, even big networks, 65,000 of them, really fast. How long does it take to put 65,000 packets on a network?
Milliseconds or
Yeah, exactly, right? So you can scan a network really fast, right? Doesn't mean that a network can't be scanned if ICMP is not turned on, because there are other ways to scan it. Huh?
There's lots of tools.
There's lots of tools, right?
We make several.
So the ICMP packet has obviously an IP header, right? Because it's a function of IP, right? What else do we have in it? Huh? So technically the header is IP, right? But we have to put some other information in there, right? We need some extra ICMP information. And if you looked at like the layered architecture, physical link network, where does ICMP sit?
above IP?
Yeah, kinda. It sits like right here, the very top of the network layer. It's implemented as ICMP is implemented as part of IP, right? But technically, it provides functionality outside of what IP was intended, so they're two separate protocols. But it's routed through the internet through IP. So this extra little part necessitates that we also have a bit of information, because we would like to know what kind of error we had. And so the error is, it's the type, code, and the checksum. And the type and code is what we just talked about, which are destination unreachable, which is 3, and the code is 1 or 0, depending on other little tiny pieces of information you're going to send in. These are bytes, right? It's not big fields. So, and then a destination unreachable for a fragment, which is obviously the same type, different code. Time exceeded, and echo, right? And the numbers are unimportant. If you're actually looking inside Wireshark, it's just going to tell you anyway, right? So we put that in there, and then what else would be helpful in there? The payload, right? What's the payload in an ICMP packet?
OS dependent.
Well, yeah, it would be router dependent, but, or OS, whatever whatever box that happened to send that, but what would you be most useful to put in there?
IP data.
The first part of the bad IP packet. So if you have the bad IP packet in there, you also have the original source and destination, right? You also have the size of the packet. Everything else, so that some processing could happen on the device that actually sent the packet, so that you can figure things out and correct. Or if you're writing your own protocol, figure out what you coded badly and correct. And that's about it for errors.
You just leave the payload blank if you're doing the like TTL thing, the trace route.
Correct. All right. So now we're gonna have a little trivia because there's not actually a lot to talk about on IPv6. So IPv6 was standardized in what year?
Mid-1990s.
Huh? It was pretty close. Mid-1990s is really close.
96.
No, nope, really close. 98. Fully standardized in 98. In what year did IANA, so I think we talked about the internet naming authorities. Right, so there are organizations that actually hand out IP addresses, public IP addresses, right? Started out with one, then we divided it into having one as a parent and 5 basically different continents. And then they had a block of IP addresses and they handed them out. So what year did we run out of IP addresses? Or have we run out of IP addresses in the parent organization? Oh, yeah.
They were close to running out from IP.
04.
Huh?
04.
IPv4.
2004.
So they were really close in 2004, but they actually ran out in 2011. Totally out for the parent organizations. And then and so that was February of 2011. And then Asia, so remember when the internet was first developed, right? Asia was relatively undeveloped. Now we have a number of countries there that are very, very developed. So they were the first to actually run out of IP addresses. So that means they have no IP addresses to give to anybody. What year did that happen? So this was February of 11. It happened in April.
2012.
April of 11.
Nice, 2 months.
Seriously don't have any more IP addresses, guys. So then when did Europe run out?
May.
A month after.
9 of 12. And then when did there's also ARIN, which is US, Canada, and Antarctica. LATNIC, which is Latin America, and AFRINIC. When did they run out?
I like that we included Antarctica in our group.
Can't put a flag there, but we're gonna claim it anyway.
2013.
So all of them finished running out in 2015. So in 15, we are completely out of IP addresses. Now, in 98, we had a solution to the problem. Now, it's a technical solution, doesn't mean that we have an implementation solution of actually deploying this solution out through the entire internet. But we have the technology. In 2015, we are out of IP addresses. By the way, if we're out of IP addresses, how can you get an IP address at home? We're out.
NAT.
Masking.
Huh? Not NAT, not masking. Talked
Parent
about this
organizations.
extensively in the beginning of.
Parent organizations are out, but Comcast isn't out.
So, well, Comcast is sort of out. The organizations are out. They do statistical multiplexing, right? Not everybody's going to be on the internet at the same time. Also, we've also had some alleviation of problems in that most cell phones actually run on IPv6. And I know that not AT&T, but Verizon, I think fully went to those addresses in, I think it was 16. I looked up a big history of it today. Right? But the big question is, why haven't we actually moved to IPv6?
Have to like convince all the private companies to spend money on making the switch, right?
You have to convince, there's no real incentive yet, because even though we're out of IP addresses, right? Not everybody in this room needs an IP address at the same time, so if statistically I only need 50%, then I have 50% more IP addresses than I thought, right? Because I can dole them out to individual people. What else?
Most sites don't have support IPv6.
So a lot of sites don't have support for IPv6. And some surprising sites don't have support. So out of the top 100 sites, what's percentage of the top 100 sites? So that's talking like Google, Facebook, PayPal,
70%.
huh?
70%.
33%.
Have
Yeah.
IPv6?
Yeah, have it implemented. 33%, and that was an article that was in September,
What
right,
sites are you
of this year.
including?
So it's very recent. 33%. Out of the top 1,000, how many have it?
10.
It really close. I think it was 12, right? But out of the top million.
One.
Yeah, so you're getting the idea, right? So right now, if all of us decided, if Comcast said, you know, we are not going to issue any more IPv4 addresses for you, deal with it. There are sites you couldn't reach.
So, what's the major downside to switching from an IPv4 to an IPv6 based on application, like industrial applications? Does it really make a huge difference?
So there is some arguments for IPv6 that obviously the traffic's a tiny bit bigger because you have a larger address space, and there might be some performance issues with that. There are some things that are out on the internet that can't really be upgraded. They are what they are, right? So if you think, like, let's say I have a box, an industrial control system that's IPv4, and this is not super realistic because most of these things don't actually communicate on IP anyway. Like most industrial control systems work on Ethernet and not IP. But let's say you had a box out there, somebody developed it, and is sitting on IPv4, and the company's no longer in business, and there's no source code available, right? And it's an industrial control system is controlling a power grid or a nuclear power plant or something, right? Probably don't want to shut that off because I'm sure there's some data you need from it. Hopefully you're isolating that data from the internet, but in my experience they're probably not. So, but you can't just turn it off, right? So in order to implement IPv6, what do you have to do? You have to put a middle box in front of it, right, to assume an IPv6 address and then translate that to IPv4 traffic and back and forth, right? It's sort of like NAT but in reverse, right? You're taking a larger address space and making it a smaller address space.
So the normal operating systems do that, it's like the Windows.
Correct.
operating
So
system.
Windows has had it since like 2000, 2001. I think all the OSs pretty much have had it since '08. So that's not a problem. The problem is the rest of the core of the internet. Right?
Well, if you assume that both ends are IPv6, okay, are we gonna have like a better performance compared to the IPv4? Because from what I read, the header format is much similar than the IPv4.
The header is way simpler than IPv4. Way simpler. But the address space is bigger, obviously. But like, let's say A wants to talk to D again, and they are ahead of the game, high technology. If A wants to talk to D, then this link in IPv6 has to be what?
Has to be IPv6.
It has to be IPv6. Is there a way we can cheat?
No.
Yep.
Sure,
Yeah.
we can tunnel,
Mm-hmm.
right? Tunneling presumes that this box here, right, which is probably some kind of gateway, and this box here is some kind of gateway. And obviously,
This is
there's many, many more boxes than 2 in here.
Mm-hmm.
What do we do for this?
Encapsulate.
We encapsulate. We can encapsulate and tunnel it right through, and then it appears on this side as IPv6 again. It takes more work for the 2 boxes because they actually have to change, they have to actually add headers, right? These aren't quite middle boxes because they're adding headers and not changing them. So it adds this box adds a header, this one rips it off, right? And the other way adds a header and the other one rips it off, which happens in the layers all the time, right? We talked about it going through like a PPP tunnel, right? It adds a header and then rips it off on the other side. So, as of the writing of your book, which was, or as of the writing of the instructor materials for your book, which was 2012, I think your book is actually 2010, we had 1% of the boxes on the internet in IPv6. 1%. And take that with a grain of salt because this is like user boxes, not necessarily like IoT devices. And the way they measure that is Google measures it by traffic coming through Google. In 2000, right now, as of today, how many do we think we have? We looked at it today.
So 1%.
Huh? No! Thank God, no!
2%.
Huh?
It's double.
So it was at 1 in 2012, and today 20%. Today's is 20%. Right, so we're on our way. And if you look at the curve, it looks like the curve you would expect, right? It is, probably the final curve will look something like this, right? Where there's some point right here where it jumps up to 100% because they just simply turn it off.
What is that 11 to 20%?
Huh?
What is it?
20% of the user boxes on the internet are on IPv6. And that's because a lot of countries that are not the United States have actually implemented it and use it in their actual ISPs. So when you go and get, what are some advantages over IPv6? It has a much simpler header, right? We can talk about the header, but it's super simple. What else?
More addresses.
More addresses. How many addresses?
Way
Yeah.
64-bit versus 32.
Huh?
Yeah, it's 2 to the power 128. So
It's 2
there's
to the
no-
power of 128.
Yeah. Is there a name for it? I don't think so.
More than
It's 128-bit addresses, right?
Mhm.
So,
Isn't it something like you could assign an IPv6 address to like every atom on Earth and not run out or something like that?
I don't know exactly, but to give you an idea how big to the 128th is, I did this for a forensics presentation because it also happens to be the collision space for MD5. So MD5 is used widely in forensics. So to give you an idea how big that number is, it is 50 million times the width of the universe if the universe is 15 billion light years wide in inches. It's a really big number, right? So it is on the scale, don't quote me exactly, but it's on the scale of grains of sand on the world's beaches, right? It is a large, large number. So, but that's actually the range space. Technically, the actual, the space is only 4 times bigger, right? So we had 32 bits, we take 4 of those, right? Put them together, and we can hold a 128-bit number. It's the range that's big, right? So you can, presumably they picked that number. It's actually a very common number in computer science, right? 120-bit of most of the encryption algorithms that are in use today are 128-bit encryption space. Why? Well, it's a nice, easy power of 2, which makes it computationally easy. But also, it's a significantly large number. So just think that, not even talking quantum computers, if there were 2 to the 128th bit machines on the internet, and you were able to compromise those or whatever to get enough of them to work in concert, they could compromise all current encryption in 2 cycles, not 2 clocks, right? But 2 rounds of encryption with 2 ciphertexts. It's a lot of machines. 228-bit number is so big that it's thought that it would take every machine on Earth more than 1 million years to crack that, right? So now I'm saying you can crack it almost instantaneously if you had that many machines. So it's going to last a while.
Hopefully.
Hopefully. Because if it doesn't last, right, and don't get me wrong, there's some administrative things that we could do to really mess it up, just like we did with IPv4 and set out blocks of addresses for here, and so we actually have a much smaller space. But just that number, presumably, right, unless we are now conquering the galaxy, we probably have enough space to hold all the computers. Right? It's a big number. But they thought 32-bit was a big number too, and we never get there.
When every grain of sand is tweeting, come visit their people.
Exactly. Now it's tweeting its current temperature and or whatever else, because if you had that kind of data and the kind of processing power that was necessary to actually act on that data, then just think of what you could do with simulations of weather modeling and predictive analytics would be ridiculous, right? So they'll find a way to try to get there. So instead of the dot notation, it looks a whole lot, if you look at notation for it, it looks a whole lot like MAC addresses, except for you have 2 You have 8 of these. So you have very large address spaces. They're much harder to read from a human perspective, but the computers can handle that just fine. And we can, what we're going to talk about right next is NAT. We can completely do away with NAT. Right? Every machine can be connected directly to the internet. Yay, right? Field of targets to hack. It's common for, in these types of notations, let me do another one. No, we just look like that. To shorten them. So this address, presuming all this was zeros, would look like that.
So if we do away with NAT, if we remove NAT from the equation, what happens to virtual networks whereby you have virtual machines within a host computer? Are they going to connect directly to the physical?
So they could connect directly to the physical, but presumably you want that still to go through a gateway.
Right.
Right? And there's nothing in IPv6 prevents tunneling. Right? All think of it is, for all intents and purposes, is we take IPv4, we simplify the header and get rid of a lot of stuff that we don't need in there. Add actually a little bit of stuff in there, a bigger space for quality of service, which we can also use for security, and make the addresses really big. But in functionality, it works like IPv4 in a hierarchical network, right? Network, computer, so that we can route our way through the network. So in a virtual private network, which we will eventually talk about, you simply fake the network you're on, right? There's a box that fakes your network. And you connect and there's a tunnel through it, just like there would be for VPN on IPv4. So the big question is why has it, and we've talked a little bit about this, why can, like, we develop protocols all the time at the, a new version of 802.11, new application protocol on top for streaming content, whatever. Why is it taking what's the fundamental problem that is taking so long for IPv6 to be implemented? So it's because it requires everyone to use it. All these other protocols, right? If 802.11n came out, right, doesn't mean that you have to go out to Amazon or Best Buy if you're old school and buy yourself an 802.11n router to get on the internet. You don't have to, right? Your old stuff works fine. You may decide that you want it in, or for whatever reason. At the same time, if there's some new streaming protocol, a new peer-to-peer network, or something that's sitting at the application layer, you also don't have to go out and get it right now, unless you want that very particular service. IPv6 requires us all, and the first rule if you have a good idea, is if you say if everybody would, you've already lost, right? To give you an idea, IPv6 is fundamentally better than IPv4, and it has been in existence and standardized since 1998, which was quite a long time ago. I wish it was when I was still in high school, but it's not quite that long ago. But it's quite a long time ago, right? We will have, just think about it, next year is 2018.
20-year anniversary.
It is the 20-year anniversary of the standardization of our new technology. Because everybody has to implement it at the same time. And on top of that, there were other technologies that made that address thing not so much of an issue. We ran out of addresses in 2015, but we can do some multiplexing, and that also the number of addresses on the internet does not represent the number of machines on the internet. There are a vast number of machines on the internet that don't have addresses. How? You have to have an address to communicate on the internet. We say it's on the internet. It has to be able to do IP, but there's no addresses. How do you do that?
We can have one one public IP for several computers.
We have one public IP for several hundred or thousands of computers. We can put entire networks with one public IP.
Just called PAT, right?
Huh?
PAT?
It's called NAT.
Well, NAT if it's one-to-one. If it's a one-to-many, we call it PAT, because we're gonna use one IP address plus port number to identify that host.
Correct. So, yeah, the book identifies as a NAT, but you're correct.
Okay.
It is a combination of when we say NAT, it's a combination, like your NAT router at home, is a combination of one IP address, one public IP address, and then we'll see how we use a table in combination with ports. And I mentioned this a couple, like last week or the week before, that it's really just port mapping, right? So the problem is it breaks our layering protocol. We have built our entire networking class on layering, and that breaks it. It breaks it because it doesn't add an IP header. It rips the IP header off and replaces it, which breaks our layering protocol. Right? There are other, and we call these middle boxes, there are other things that do this. Right? What other things break our networking protocol? Or layered network?
Well, not everyone will have a real IP.
Yeah, so NAT absolutely breaks it because not everybody has a real IP. And we'll see how that actually breaks it. Let's actually just talk about that right now. Remember, we built a network. And we've been building this all semester so far. Right? A talks to some middle machine B, which talks to some middle machine C, which talks to a destination D. The beauty of this layering is that A can talk to D and D can talk to A without knowing what's in between B and C. Now, let's say that this is now going to rip off the IP header. So internally we had a let's just do 10 because it's small. We had a 10.0.0.2 address, right? Our internal IP address here is 10.0.0.1. Our external IP that we got from our ISP is 42.42.42.42 because it knows everything, right? So our packet comes in and we have an IP header and we have a payload, right? What's our IP header?
10.0.0.2.
It's 10.0.0.2 and we'll just call it D for right now, right? So it's 10.0.0.2 and D, whatever that IP address is, right? It sends it here, right? It rips off this header and replaces it with its own, which is not its internal IP address. It's our 42 to the fourth, right? So if 42 4 times, and then D. Now we can make it here because we have a public IP address and we can get it through the internet. Now D sends D acknowledges the packet. What is its IP header?
42.0.4.
It's D and 42 4 times, right? So now we end up here again, and now B needs to remember where A was, right? So we have to build a table. This breaks our layering protocol because what if D needs to send the first packet? This is no longer a symmetrical network, right? Packets can only originate from A. Now we can do some mapping to say, oh, if it comes in on port 80, which is web traffic, it always goes to A. If it comes in on 21, then it always goes to B, right? What happens if you need 21 traffic to go B and A? Because nobody SSHs into more than one machine in a network, right? It breaks the layering. So now, if you need to SSH into two machines, you either need to put weird ports for SSH, or if you have more than one web server, you have to put weird ports for your web server, or you have to tunnel into that network and act as if you were there. It breaks the symmetry in our network. A can easily send to D, and we'll build tables to show how that works. D cannot easily send to A.
Not
So-
as the initializing box.
Huh?
Not as the initializing.
Not as the initializing box. First packet. Why does it work on the second and subsequent packets?
Just B knows.
It's saved in the flow table.
Yeah. So much like when we were building tables for Ethernet, and where a packet comes through and you automatically discover because the packet's coming through the first time, right? We can build an incoming table if that packet's already come through. But there's no way for D to do some kind of broadcast across the internet to discover where A is. Right? I don't know if you would want to be able to broadcast across the internet and reach every computer.
So you can only just respond by acknowledging after because the first packet.
You can only just respond. And so this is how it actually works. So we're going to call these IP addresses letters again because that's so much easier. Right? So A sends a packet to D. And it sends it on port 42. 42. Because that's in our dynamic range. And then it reaches here at B. B rips off this header, including the port, but stores that in a table. So A is talking to D on 4242. And then it rips that off and replaces it with B is talking to D at 1500. So now the port has changed. This is an outgoing port, so it's dynamically allocated. It's not a special port, right? It reaches D, and D replies to B, not A, because D doesn't even know the existence of A. It replies to B, hey, some other packet comes in, and when the packet comes in this direction, it rips off the IP header again and replaces it with A is talking to D at 4242, and it goes back. Now, I only put the outgoing port, right? Presumably D has some kind of service, which means that A is talking to D on 4242, and that service is port 80, web traffic. So there are actually two ports, right, in the header. So D gets it and sends back, okay, normally it doesn't, it's not gonna send it back on port 80, it's gonna also pick a dynamic port and say, hey, this is the channel we're gonna communicate on, for instance, for web. Because presumably D wants to talk to more than just A, if it's a web server. And we just simply start building tables back and forth, back and forth. Now this actually works if there was a B on the network too. Let's put A sub 1, we already have a B. So A sub 1 is on the network too. It can talk to B, and it can actually do it on the same, let's say it's gonna talk to E this time. It can do it on the same port, 4242. A sub 1 and A don't need to know that that have exclusive rights to ports, right? Because it's a combination, like was said up front, it's a combination of port mapping, port and address mapping. It's not just address translation, we're translating ports as well.
So is that how you get around if both A and A sub 1 were talking to D and they were looking at a web page on D?
Correct.
That they would be from different originating ports?
Or combinations of address and ports.
I have a question.
And the second one-
So after it went to the D, what happened? They got lost.
Okay, so A
Step by step.
talks to B, sends a packet to D,
Okay.
right? B intercepts it. It's talking on 4242, which is an outgoing port, to port 80. Right? So then B remaps that to itself, and D talking on 1500. D, and remember, that's the outgoing port, not the not the destination port. It's the source port, not the destination port. Then D replies on 1500, because that was the port that the originator said, hey, this is what we're going to talk on. It gets mapped back to 4242 and goes the right one. Right? If on this one, B would not reuse 1500, what would happen if it reused 1500? It would have no idea where to send it back, right? So it can't use 1500, so B is going to talk to D, and the destination port this time is going to be 1501. Oh, sorry, E. But even if it was talking to D, right, it would still have a unique mapping. Now, how many can we map? As many ports we have, which is what? Round number, doesn't have to be 65,000. We can do 65,000 unique connections.
We can connect 65, but we only have 49 available.
Correct. Well, everything past
Because this year, 2023 is the reserve.
is reserved.
So 2024 to 49, 151, 152 is the dynamic ones.
Yeah. So,
It's, yeah, I can't remember the
so
third group.
those are the standards we can still use. I wouldn't recommend using anything below 1024.
Another question. After you send it back, why would you communicate?
So, okay, so let's say that D is an endpoint, so we'll put E here. So this came out A to E off of 4242. It maps it from B to E at 1501. So when this receives the packet, it thinks it came from B on port 1501. So then it replies from B to 1501. It comes into the box. It says, oh, 1501 is mapped to A at 4242, and or A sub 1, and replies to A sub 1. But it breaks a lot of things. Because in all our other layering, we were simply adding headers and ripping off our own headers, right? We never changed anything. And so since we're now changing things, we have things like is no longer symmetric. Also, there is obviously some processing that has to go in there. But there are major advantages. The first one for NAT was that it alleviated our pressure. The most obvious disadvantage is that it also has delayed IPv6. Somebody said that right at the beginning of class. Why we have not implemented IPv6? And the answer is NAT. It alleviated our pressure. Now we can have very large networks, really big ones, behind a NAT, so long as the traffic is still bursty, and we can do these mappings. And we can they either disappear with timeouts, which is less optimal, but is necessary for some protocols. But in a connection, you can simply wait for the connection to be torn down and then rip it out of the table. in any connection-oriented protocol.
Question, what's the reason behind ripping off a header?
So, technically, you could, let's think of what else we could do. We could wrap a new IP header on the old IP header. There's a problem with this. So if we wrap a new IP header on an old IP header, what is the problem? And it's not totally intuitive.
On the response, you don't really know. D doesn't actually know where it's sending, so B gets it and pulls the header off.
B gets it, pulls the header off, right? And then what?
And it won't be able to respond back.
Yeah. So did D encapsulate the IP address in there? Okay, so now we could build a fancy protocol on top of that, right? And say, hey, we're going to have the NAT protocol rather than a middle box. And so we're going to say, hey, if you receive this type of packet, now you got to build IP headers in it. So it makes it a much more complex problem. There's a more bigger problem with that. If you're going to wrap a header, it necessarily makes the data bigger. What if we have a DFlex set? Oops. So the router responds. Remember, the packet guy, the router is bigger. It reaches a router someplace in the internet. And imagine if you did this protocol, then they're not just edge boxes. They could be anywhere, right? Because it's a protocol, and we're trying to build it into the network. And now you reach a box, right? And now you have to do deep packing and inspection to be able to say, well, my MTU is 1500, but I really need to tell you that it's 4800, or really need to tell you that it's 1400 because I have this other IP. I mean, you can start to see where you're putting a lot of load on the inside of the boxes. Right? So it was, when that came out, it was hated. It's not necessarily loved today, but it was decided to push it as far to the edge of the network as possible. And if you rip off the header and replace the header, then the rest of the internal functionality of the network will work. Doesn't necessarily mean everything's going to work great on the other side of it, on this side, but on this side, everything is symmetrical still. Don't have to do anything special. Don't have to put any extra load, nothing. What are other middle boxes that we use all the time, particularly in enterprise?
Firewall.
Firewall. Why a firewall?
Because it's always at the edge of the network.
It's on the edge of the network, and it breaks layering. How does it break layering?
Because it rewrites the header.
It can, yeah, right? But so there are a couple things with firewalls, right? Firewalls are pretty simple devices, but let's take something that's even more complex, like an intrusion detection device, right? So if you have intrusion detection middle box sitting on there, or intrusion prevention, it has to do some crazy things, right? Because you might not know without actually pulling out the entire flow that something is malicious, right? So it reassembles packets before actually, and it can either sit off the network or it can sit in the middle of the network, right? So it's reassembling packets, looking at them with deep packing and inspection, and then breaking them back up so that they can make it to the next place in the way that they should. There are all sorts of crazy things that can happen. And while those are very useful, particularly from a security perspective, remember I told you that security broke the layering completely. Security breaks the layering. Because the layering is meant to abstract data from the network, but security is meant to see through the abstraction, right? Otherwise, your attacker could have just abstract their attack. That's it. We are done, other than routing, we are done with networking, for the network there.
I have a question.
Sure.
It's based on the science.
Mm-hmm.